All right, so when we're talking about capacitors, capacitors are measured in one of two units. Usually they're measured in microfarads or they're measured in picofarads. They have values that will be into the realm of nanofarads. They will have values that get into the realm of millifarads. But generally, all we're going to see things labeled in is either microfarads or picofarads. The cap meter that we have in the lab, that's what it'll show you in. It'll show you units in microfarads or units in picofarads. And I think it goes up to, when it crosses over 10,000 picofarads, then it shows the value in decimal of microfarads. So when we look at a capacitor, a lot of times when we have it, we'll have the electrolytic, which are going to be the cylinder-looking ones. They're going to have a stripe down one side. They've got a shorter leg and a longer leg. Okay? When you look at these guys, it's really nice. These are labeled as such. 100 microfarad, 100 volt, 50 volt, whatever. Those voltage ratings that's listed, that's the maximum voltage you can put across this thing, forward. They do have a polarity. The stripe and the shorter leg is your negative. The other side is your positive. If you put them in backwards, you can blow them. Usually it is. And so with this has 100 volts, but this is 100 volts when it's put in properly. When you put it in backwards, it may only have a 50 volt range. You have to kind of look up the specs for the capacitor. The other type of capacitor that we're going to look at, they look like a big square piece of gum. Okay, big green piece of plastic, orange piece of plastic. The colors don't really matter. But these guys do not have a polarity. You can put them in either direction. And what these guys will have on them is like a code. So if this one has a 104, and then somewhere down there you're going to see like a K or a V or a G or some other letter. What these are is this is telling you the value of the capacitor. So it's 10, the first two digits. Then we put 4 zeros after it, and it's measured in picofarads. So 104 is 100,000 picofarads, or 0.1 microfarads. Because if we move to nanofarads, it's 100 nanofarads. But we don't use nanofarads to describe capacitors. It's either micro or pico. So we either report it as 100,000 picofarads or 0.1 microfarad. It's just not a common, I don't know why. It's just how everybody decided to name them. The 4 is the number of zeros you put in after your digits, and it's the number of picofarads. Again, somebody who decided to label these, they came up with this, and they said, this is what we're going to use, and the rest of the world said, okay. Same thing. Yeah. Like you'll see a 472. Same thing. You're going to have 47, 2 zeros, in picofarads. So 4,700 picofarads. The letter that's on these guys, depending on the manufacturer, but they do have some general standards that they use based on like the shape. If you have the round ceramic, it's going to mean one thing, but if you have kind of the boxy, looking like a piece of gum, it's a different one. But this is the voltage rating. So I can't remember which letter is pretty standard. It's like K or J or V or something like that. It's about 100 volts. 100 volts, 50 volts. It can handle easily before these guys will explode. The ones that we have, I've never seen one of these capacitors blow up. It's usually these guys that blow. Do what? I will say it. I got to grab the stuff after a break. So we'll blow up caps then, and then I'll also show you the timing constants on a scope, so you can actually see those guys. I'll try. Those ones don't blow very easily. These ones are really easy to blow up. You put them in backwards, crank the voltage up, turn it on, and go poof. They're easy to blow. Most of the time when you blow up something in the circuit board, it's these guys that have blown up. Hmm? Yeah, I think that was the first resistor we lost too. We're going to be losing a whole lot more caps, a whole lot more fuses, and a whole lot more everything in about 6 weeks. When we start getting into power supplies, that kind of stuff, you're going to start blowing things left and right. So what I would do is I would probably buy fuses for your DMM now. Get them ordered, get them here on site so you have them, because I guarantee it, you're going to frickin' blow fuses. Radio Shack, Amazon. I mean, you can order them pretty much anywhere. Yeah. So I can go grab the package too of the ones that I ordered, but you want 0.2 amp, I think 125 volt, and I think it's 25 by 3 millimeter. I think is the ones you want. Yeah, and if there's an option, get the slow blow, because it'll, even if you just barely peak over 200, it gives you a chance to recover. Versus if it, as soon as it hits 200, it's gone. Slow blow are nice, is they offer just a little bit of a delay, a little bit longer time before your fuse blows. So it protects it against real sudden spikes, but if it's consistently high, it will still burn. Plus, I think the slow blows are a little bit better at blowing at 200 instead of approaching 200, where the fast ones usually pop right before you get to 200. A little more accurate. Mm-hmm. Just gone. And it's not that big of a filament anyway. Like if you look through them, it's hard to see it. Yours has auto fuse. It's just built different. So that's why I like that one, is because I don't have to switch the things. All I do is I switch the dial, and then internally it reroutes it where it needs to go. Plus it has a higher rating. I think yours is like 500 micro or 500 milliamps instead of 200. So, but yeah, the DMM I had in this program was from the Radio Shack. It's like the one Carson has right now, but it's that's the one I use. All right. So any questions about the markings of capacitors? I realized today when we were going into lab that I forgot to cover how we measure or how we understand what these values are. You got a question or? Capacitor? They're a 66 microfarad. 6,600 microfarad. What would theoretically this being used for? I'm getting anxiety. Are you bringing hyper coal or what's the deal? I'm asking for a friend. I'm not doing anything. I'm asking for it. Okay, theoretically, you're doing something. Yeah. There's a lot of stuff. Holy crap. Yeah, you can actually find them. So here's the thing. They're not terribly expensive, per se. The ones I found on Mauser they're about this big. They're $12 a piece. Yeah. So Mauser, DigiKey. Other than that, I don't know if we even have that size around. You're gonna have to get a special box for that. I don't remember. Okay. So that is capacitors. Now the next part, that is honestly one of the kind of the cooler things that we have that we can control. Relays. So a relay is going to start out like this. It is like a light bulb. Okay? Inside, what we have is we have an inductor. This is the schematic symbol for an inductor. We will be talking about them week 3 of next semester. So really all it is, it's a coil. What? That's the inductor. No, just the coil. So what happens is we have a coil of wire. When you run a current through a coil of wire, it's going to create a magnetic field. We're going to have lines of flux going through here, but basically what it is we're going to create a magnetic field that's either going to pull or repel a material. So inside this, we have a pivot point. We have a contact that comes up. We have a little spring attached to a post. At the very top, we have a contact point. And then we have a connection that runs off here. This is called our common. We have a contact point that runs off of this guy. We have a contact point that runs off of here. Depending on the relay you're using, the ones that we have in lab that you guys will be doing the first week of AC next semester, there is 3 contacts inside the one relay. So you would have a switch that has 3 different connection points. They all share the same common, but you have different sets of normally open, normally closed. So the idea behind this is you have 2 states for this relay. Normally closed, normally open. So what you do is in this state, you have, and your relay will tell you what is its base state. And it's going to be one of these 2 connections. Is it normally closed or normally open? Well, what do those mean? What's the difference between open and closed? High resistance. Yeah, closed is a complete circuit. The open is not a complete circuit. So if we had over here, let's see. If we had this connection like so, and maybe we had like this. So we have a red and green. Or let's switch those colors. This is red. This one's green. So what would this circuit be doing? When it's normally closed, the red LED is going to light up. Okay? When we close this switch over here, so switch 1, when we close that, we're going to energize this coil. This coil is going to have current flowing through it, going to create a magnetic field. It's going to grab hold of this arm and pull it this direction, which then is going to physically make a new connection over here. It is. That's all it is. It's a big electromechanical switch. Okay? So now, our normally open size, when it's energized, now we have this coil turned on, our green light's going to turn on. So this could be the startup for our machine. We want to have an indicator to tell us, is this machine on or off, or does it have the ability to turn on or off? Yes? As far as what I'm trying to frame the question. Okay, what if we had 120 volts on this guy? Do you want to be the one throwing that switch? What if we had 200K? Okay, so the idea is, you're right, it could be the last time somebody flips the switch. But the idea is, we want to have a system to where we don't have to worry about this controls. A lot of time we have different circuits. 120 AC. We have 220 AC. This could be what starts up our pump. Okay? We just don't want to have to deal with even trying to touch this 120 or getting involved in there. So we use the relay to do it. We turn the switch on, and this one we can use a 5-volt signal. We could use batteries, things like that, and we can control 120 volts. Because this, you run into shock hazards, you run into all sorts of different things. It's just easier if we don't have to deal with it.
So that'd be why it's like all the time.
Mm-hmm.
And then you would just be able to operate switches back and forth, kind of like a little controller, really, just by flipping the switch.
Mm-hmm. Yeah, that's all it is. It's a control.
How would that electrical switch back and forth?
So with this guy, so when you take the switch off, okay. So if you turn the switch off, you flip the machine down, current's going to stop. You have this magnetic field is going to slowly collapse on itself because there's nothing building it up anymore. Once it drops out of the way, this spring will physically pull it back. The cool thing is this magnetic field is going to linger. It's going to try and hold on as long as it can. And it actually is a lot slower to release than it is to click over. And what's cool is you can physically watch these guys and you can hear them. Some of the relays, Seth, that you've been working on, can you hear them when they fire?
Yeah. Actually, but like you hear the whole cabinet click and bang, and there's like 30 relays in the box. So yeah, they're kind of cool.
So if you get it real quiet, that's the mechanical click you're going to hear as these things are going. So that's one of the tests you can check to see is my relay working? Can I hear it or not? One of the things you'll have is this little contact point down here can fail. That's one of the common areas for it. The other common area is your coil of wire. Sometimes you'll burn it out. You'll put too much current through it and you'll burn this coil out. Do you care if I pass it around? Oh, those are nice.
Yeah. So a lot of the times what we have to do is when they break, we have to go and take paper and rub it in between the contact points to get carbon off of them.
Mm-hmm.
So
That's another common failure point. So you've got this hinge, you've got this spring, you got the coil itself, and you have these contact points. Those are going to be usually your common points of failure for a circuit. And like what Seth was saying, they have to go in every so often and clean these contact points out. Because what happens when you suddenly put two pieces of metal together? You have a little bit of an arc. Okay, you're going to get within that realm that it's going to arc. Okay, when it pulls apart, again, you're going to have a little bit of an arc. And when it arcs across something, you're going to start to carbonize the electronic components. Dust and dirt, water will get in there. And when it gets hit with that much electricity, it breaks down and turns into a layer of carbon, which is an insulator. And so with relays, the whole idea is we're using them as a switch. We want to be able to use a low voltage to control something else. It has dopants in it. So just like with the silicon, they input iron, boron, different materials to make it able to conduct. So that's why they call it a semiconductor material. Because naturally it doesn't conduct, but you can insert things into it and make it conduct. And it's one that you can be remelted, reformed type of a thing to absorb those into it. So it's not like screwing a nail or screwing a screw into a board. The screw becomes part of the board. Yeah, reincorporates it. That's a good way to put it. Okay? And really, that's the gist of relays. That's all they work. Now, one of the things you're going to find is all these relays are going to be rated for different voltages. They can handle 120 volts. They can handle up to 24 volts. You have to look at the specs. You also have to look to see how it's wired. One of the things also that you need to understand is how much current does it take for this sucker to engage? Part of the lab is figuring that out. How much current, how much voltage does it take to get this thing to engage? And then once it's engaged, what's the threshold that it has to drop below before it shuts off? Because it still has a little bit of pull, but eventually the spring is going to have more force on it and pull it tight. With relays, there's not a lot of serviceable parts in there. Maybe these contacts sometimes, but the ones we have, they're fully encapsulated. And they're designed, once they break, they break. You throw them away and get a new one. Looking at them, you'll have to find wiring diagrams. And so usually what you'll get, the ones that we have, there's a couple different flavors, but one of them is going to look like this. And what you're going to see is a drawing that looks like this. So you're going to see the post with a key to tell you how to orient this thing, because if it doesn't have the key, how many different combinations, if we have 13 pins, how many different ways can we put that into the circuit? 13 different ways. We can turn it every which direction. So on these guys, they usually have some sort of a key, so that way the same contact points goes to the same circuit. So when you look at the schematic, you're going to see on the bottom it's going to give a physical representation of how things are wired. Then you're going to get a schematic, kind of like this guy. It may or may not show your contacts. They look like this. You're going to find a place that's connected together. You're going to find places that are open. They're going to be labeled as normally closed, normally opened. There's not real one set way a schematic has to look. So there's multiple ways. That's why I'm showing you all the different pictures, the signage, that kind of stuff. And then what you'll see is you'll see pin numbers. So like this is 10 and 11. This guy is going to be 1, this is 5, and the common is like 6. Okay? If it has multiple outputs, you're going to see multiple contacts that have normally open, normally closed, and what set they belong to. So this would be like normally closed 1. This is normally closed 1. So those two are a pair. So if you want a circuit to operate in either one condition or the other, you would use that pair. If you have 2 or 3 different circuits that you want to have switch at the same time, you would use like your normally open 2, normally open 3. And so it just depends on the use. But on the schematics, these will all be labeled, and it has the little numbers off to the side. Part of what the lab is looking at the schematic, looking it up, and deciphering what is the picture trying to tell me. Yes. Actually, week afters. This is the first part of the AC lab. Do what? Yeah, you'll still be using DC. So just for the first day in lab of AC, you'll still be coming back here. That's just to kind of push us out a little bit so you have a little bit of time to learn what you're going to be doing in lab. Any questions about relays? Mm-hmm. Connections it has. Mm-hmm. Yeah, like yours, I think one of them looked like it was a 3 set. So like this guy, this one's got a ton of connections. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this one has 12 sets of normally open, normally closed contacts. One of these is going to be the ground. Probably this guy, I would imagine. One of these is going to be power in. One of these is going to be power out. Let's see. These are for your coil. And then my guess is somewhere in these are not connected, so not all these pins. So like here, this would be for your coil. This would be for your connections, and then probably one of these sets is your common for all these guys as well, that everything's going to be run into. So this has, 10 to 12 different relays that can be all triggered at the same time.
So you would just wire another one in backwards if you wanted it to shut off when this came on.
You just would use the different set of pins because you have a normally open, normally closed. So if you want one to be on, one system to be on, you wire it up to the one side, normally open, normally closed. Wire the other one up when you want it to run. So you could have, with this guy is, like with our red and green, when the red light's on, we have maybe just a cooling fan running, okay? Because we want to keep, we want to cool it down after we're done. So this side's going to keep the fan running. When we fire it up, it's going to fire everything up. When we turn it back down, this normally closed is going to re-engage the cooling pump. Kind of like an idle cooling pump. This will have its main, while we're running, we want to put a lot more for it, so we're going to switch to a different system. Relays are fun. What you're going to find too is, like I said, so this is a mechanical switch, or an electromechanical switch. These are just regular mechanical switches. Okay, we have to physically toggle them. This one we can use electronics to toggle the manual switch. When you guys get into transistors, JFETs, those are electrical switches. It only uses the electricity and electronics to fully switch circuits on and off. But they all kind of do the same thing. Transistors, generally, you use them as a switch. You either have them fully on or fully off. There's very little in between. Questions about these?
Do capacitors have other uses besides the timing?
Filters is the biggest part. You use it to filter out certain frequencies. You use it to hide things.
Oh, so that's like AC.
DC, it's pretty much, a timer and or like a timed open type thing. So if you want voltage for a little bit of time and then you want it to go away on a pin, you'd put a cap in and it would charge, and then you don't have to worry about it. Okay. Questions about relays? All right. Now we're going to move into everybody's favorite, math. When we get into the AC world, and like what we talked about, is we're going to have a range of imaginary values. Okay? This is how capacitors and inductors work in AC. They have a resistance that gets formed when we run a frequency through it. But there's no way to measure that resistance physically. Like, we can't just hook up an ohm meter. It only exists when the frequency and voltage are present. But we can see their effect on the circuit. So if we put these guys into an AC signal, the resistances we can control with the frequency, and we'll see them change just like as if we had a resistance value in there. So when we look at it, our x-axis is going to be our resistance. This is our real value. This is 0. We don't have negative resistance. Okay, resistance is always positive. No matter how we calculate it, the negative portion is going to be the voltage and or current. Okay, at the top of our y-axis, we got to be looking at positive reactance, positive J values. On the other side of our y-axis is negative reactance and negative J values. So when we solve for these guys, we're going to come up with a value. The negative J's is going to be the realm where our capacitors live. The positive J's is where inductors live. When we put them together, we're going to get kind of a net combination of the two. So what we're looking at is we want to find total resistance to current in an AC circuit based on our inductors, capacitors, and resistors. When we start in AC, we're going to deal with capacitors first. So everything is going to be in this realm. What we're going to end up with is basically a vector plot that looks like this. So we're going to have a right triangle with these angles. So this value is our reactance value. This is our real value. And the combination of the two is what we're going to call impedance. Impedance is not just resistance. It's the total resistance to alternating current based on our components, because that's going to change based on frequency. So as we look at this, we're going to be interested in a couple of angles. So we have theta and we have phi. Theta is primarily the one we're going to deal with. Phi is just another interior angle that we can label. Oh, phi. Phi. Theta. Theta. Okay? This triangle can either go up into the positive realm or into the negative realm. It just depends on what we're doing. Are we dealing with a positive or a negative reactance? Capacitors versus inductors. So when we get to these, our resistance value is measured. We can physically measure the resistance. We can't measure this reactance value, but we can measure the frequency, and we can measure the value of our capacitor or inductor and calculate this value.
So you would know the value of R and value of Z, you wouldn't know the value of X.
Well, more often we would be able to calculate this value of X, but we would know this value of R. And then Z is a calculation between the combination of the two. Let's see. So Z, we're going to use Pythagorean's theorem because it's a right triangle. So what is Pythagorean's theorem? Okay? So when we're solving for this guy, we're going to take the square root of both sides to get just that value by itself. This is going to be one of our primary formulas for solving these things. Now, when we get into these, we're not going to get into a whole lot between calculating them as far as like where we get this X value. We're going to be given these values. So we're not going to get into calculating the reactance values. So when we're writing these values, so remember when I was talking about how we have two different methods of saying the same information. We have rectangular notation. So basically we're going to give the coordinate of this point. So it's going to be our real plus or minus J of X. Because the reactance values are not going to directly add or subtract to the resistance values. They don't mix. Think of oil and water. We can get them to mix, but we have to agitate it, we have to force it to go. But by itself, they just don't mix. It's pretty cool. Okay. So this is our rectangular notation. Yep, rectangular. We're giving two coordinates. The polar notation we have is going to be our impedance value at our angle theta. So both of these guys are equivalent. If we have one, we can solve the other. Yes. I don't know. So with these values, when we're in rectangular, we can add, we can subtract, and we can also multiply. Okay? This goes back into some of the math we were doing last week, where we have a j times a j, we get a j squared. What's the value of j squared? -1. Then that value is going to change, it's going to change its sign, whatever it is, multiplied together, that's going to just turn into another constant. So we end up with a real and some value of j. If we have j to the higher power, we can always bring it down till we have at least a j value. When we're in polar mode, we can multiply and divide. And that's the only thing we can do. So we have to have both of these forms so we can add and subtract and multiply and divide. Now, the idea behind this is when we get into series and parallel circuits, we have to treat the resistance and the reactances differently. When they're in series, we add the values together. When they're in parallel, we take the product over the sum. So we're multiplying and dividing. So there's going to be times where we want our answers in rectangular, and there's going to be times we want them in polar, depending on how we're treating them in our circuit. Okay. So coming back like with our Pythagorean theorem, we have our real value squared plus the reactance value squared is equal to C. We take the square root of that. Come on. Give me the eraser. That gives us the magnitude. The problem is Pythagorean's theorem only gets us so far. It only gives us the magnitude. It doesn't do anything else for us. Well, we need to be able to know this angle. This is where trig comes into play. Welcome to trig. How many of you guys have blocked this from your memories? How many of you had a teacher say you're never going to use this again? Well, guess what? We're going to use it again. Yeah. Yep. Okay. SOHCAHTOA. You're going to remember this. Get it burned into your memory. You're going to be using this for the next 6 semesters. You are. Yes.
My teacher, like when we first learned this, like, I don't know, 8th grade, 9th grade, whatever it was, like the whole, like, beginning of the year, they're telling the story about, like, this foreign exchange friend that they had. Like, really good stories, like, it was their best friend, And then we get to the end, and we have all these stories in our head, and it's like the middle of the year, and